Look up at the night sky, and you'll see a universe that seems serene, timeless, almost peaceful, a tapestry of stars and darkness stretching into infinity. But that stillness is an illusion. The truth is far more dramatic, more violent, and more intimately connected to you than you might ever have imagined. Every atom in your body, every breath you take, every beat of your heart carries echoes of cosmic chaos, collisions of unimaginable scale that shaped not only the world we live in, but life itself. We often think of the universe as distant, separate from our daily existence. But what if I told you that the very iron in your blood, the water you drink, and the air you breathe were born from cataclysms so powerful they defy comprehension? It was Carl Sagan who famously said, "We are made of star stuff." It's a beautiful idea, one that fills us with wonder, but have you ever paused to ask what created that star stuff? What forged those essential elements and scattered them across space, eventually finding their way into you and me? The answer lies in violence, cosmic violence. Forgotten collisions between asteroids, planets, and even entire galaxies set in motion the events that led to our existence. These weren't gentle meetings. They were explosive, planet-shattering impacts that melted surfaces, vaporized rock, and seeded barren worlds with the ingredients for life. And though these events happened billions of years ago, their legacy is written into everything around us and within us. In this video, we're going on a journey back through time and space to uncover how these ancient crashes hold the key to understanding not just where we came from, but who we are. We'll explore how a Mars-sized object slamming into the early Earth gave us our moon and stabilized our climate. We'll see how a rain of asteroids brought water to our world and possibly even the building blocks of life. And we'll confront the sobering reality that the same cosmic forces that created us could one day threaten us. This isn't just a story about the past, it's about our future, our place in the cosmos, and the profound connections that bind us to the universe's most violent and creative moments. So get ready to rethink everything you thought you knew about existence, because we're about to dive deep into the mysteries written in the scars of the universe. To truly grasp the power of cosmic collisions, we must first journey back to the very beginning, to a time of almost unimaginable chaos. Picture the universe not as the vast, organized expanse of galaxies we see today, but as a seething, superheated soup of fundamental particles and raw energy, freshly born from the Big Bang. For hundreds of millions of years, there was no light, no structure, just a fading afterglow and a formless fog of hydrogen and helium. But then, something miraculous began to happen. The faintest whisper of a force, gravity, started to pull on these particles, gathering them into the first clumps of matter. These weren't gentle gatherings, they were violent, chaotic collapses. Immense clouds of gas, nebulae light years across, crumpled under their own incredible weight, triggering the fusion engines of the very first stars. These pioneer stars were behemoths, hundreds of times more massive than our Sun, and they lived fast and died violent deaths. Their spectacular supernova explosions were the universe's first great acts of recycling, blasting newly forged heavy elements like carbon, oxygen, and iron out into the void. This newly enriched material didn't just float away peacefully. It was swept up in the gravitational currents of a still-forming cosmos, colliding, merging, and accreting into new generations of stars. Around these stars, disks of dust and gas swirled, and within these disks, the building blocks of planets began to clump together. This was a period of incredible violence on a smaller, but no less important, scale. Countless planetesimals, chunks of rock and ice, endlessly smacked into one another. Some shattered, some stuck together, growing larger with every impact. Think of it as a cosmic demolition derby where the last object standing became the planets we know today. This relentless bombardment was the solar system's messy construction phase. On an even grander scale, entire infant galaxies, drawn together by gravity, performed a slow-motion dance of destruction and creation, merging to form larger structures and stirring the cosmic pot, ensuring that the elements of life were thoroughly mixed and distributed far and wide. Without this foundational era of chaos and collision, the universe would be a very different and far more boring place. It would be a thin, sterile soup of hydrogen and helium, incapable of forming rocky planets, oceans, or living beings. The carbon that forms the backbone of our DNA, the oxygen we breathe, the iron that carries oxygen in our blood, none of it would exist. The very materials that make up our bodies and our world were forged in the hearts of those first massive stars and then scattered across the cosmos by their explosive deaths, only to be gathered up again by the gravitational pull of new stars and the relentless crashing of protoplanets. This is the great cosmic paradox that lies at the heart of our existence, creation through destruction. The universe built itself through a series of violent accidents, and we are the beneficiaries of that ancient chaos. The stage was set not by a gentle hand, but by a constant, thunderous rain of impacts that turned simple elements into the complex ingredients of life. Now let's zoom in on one specific, world-altering moment, the single most important day in our planet's history, a day that, of course, no one was around to witness. Picture the early solar system, a chaotic construction zone still littered with the debris of its own formation. The proto-Earth was a hot, molten sphere, still gathering mass through smaller collisions. Then from the cosmic shadows came Thea, a wandering planet roughly the size of Mars on a fateful collision course. The impact was nothing short of apocalyptic. This wasn't a gentle nudge or a sideswipe. It was a head-on, catastrophic merger of two worlds. The energy released was beyond comprehension, instantly vaporizing a significant portion of Earth's young mantle and much of Thea itself, turning solid rock into a superheated plume of vapor and molten droplets that was hurled high into space. This ejected material didn't just float away. Held by Earth's gravity, it formed a searing, temporary ring around our planet, a torus of destruction that began to rapidly cool and clump together. Within perhaps just a single century, through the relentless pull of gravity, this ring of debris coalesced into a single, spherical body, our Moon. This explains so much about our lunar companion that once puzzled scientists. Why is the Moon's density so much lower than Earth's? Because it's primarily made of the lighter mantle material that was blasted off the surface, not the dense iron core. Why do the isotopes in Moon rocks so closely match those on Earth? Because the material that formed it came primarily from our own planet and its impactor, thoroughly mixed in that colossal furnace of impact. But the Moon's formation was just the start of the story. Thea's gift reshaped our world in profound and lasting ways. The sheer force of the impact knocked Earth off its axis, leaving it tilted at about 23.5 degrees. This tilt is the sole reason we have seasons. Without it, the distribution of solar energy across the globe would be static and uniform, eliminating the annual cycles of growth, dormancy, and migration that have driven the evolution and rhythm of life for billions of years. Furthermore, the incredible energy input melted the entire surface of the planet, effectively resetting its geological clock. This global magma ocean allowed heavy elements like iron to sink once more, forming a distinct solid core, while lighter materials rose to form a new, stable crust, setting the stage for plate tectonics and the eventual formation of continents and oceans. Perhaps the most crucial role the Moon plays is that of a gravitational anchor. Our planet's rotation is not perfectly stable. It can develop subtle wobbles or precessions over long timescales. The Moon's gravitational pull acts as a steadying hand, damping these oscillations and preventing wild, erratic shifts in our axial tilt. Imagine a spinning top that begins to wobble violently before falling over. Without the Moon, Earth's climate could experience similar extreme chaotic variations, swinging between ice ages and tropical conditions on geologically short timescales, making the long-term stability required for complex life to evolve nearly impossible. So, when you look up at the Moon, you're not just seeing a beautiful, silent orb in the night sky. You're looking at the enduring legacy of the most violent event in our planet's life, a cataclysm that, by sheer cosmic chance, forged the very conditions that allow us to be here today, gazing back at it. Just as the Earth was beginning to recover from its violent birth and the colossal impact that formed the Moon, the solar system plunged into what can only be described as its most turbulent and defining chapter. For nearly 300 million years, starting around 4.1 billion years ago, the inner planets were subjected to an unimaginable onslaught. This period, known as the Late Heavy Bombardment, was a time when the sky was quite literally falling. The evidence is written all over the face of our Moon, whose ancient, battered highlands are a cratered testament to this era of extreme violence. But here lies one of the most fascinating paradoxes in the history of our planet. This same apocalyptic rain of asteroids and comets, which would have sterilized the surface over and over again, did not just bring destruction. It also delivered the very gifts that would make life possible. The inner solar system during its formation was a relatively dry place. The heat from the young sun prevented volatile compounds like water ice from condensing near the rocky planets. So, where did all of Earth's water come from? The leading theory points directly to these incoming impactors. Comets, often called dirty snowballs, are immense conglomerates of ice, dust, and frozen gases that formed in the chilly outer reaches of the solar system. Water-rich asteroids, known as carbonaceous chondrites, also formed farther from the sun's heat. The Late Heavy Bombardment was a grand delivery service, knocking these distant objects inward and sending them crashing into the inner planets. Each impact was a mini explosion that vaporized the icy body, releasing its precious water vapor into the nascent atmosphere. Over millions of years, as the planet cooled, this vapor condensed and fell as rain, gradually filling the vast depressions on the surface to form Earth's first oceans. Our blue marble, the hallmark of life, was painted by countless cosmic collisions, but the delivery didn't stop at water. These carbonaceous chondrite asteroids and comets are now known to be rich in complex organic molecules. Scientists analyzing meteorites, which are fragments of these ancient bodies, have found a veritable soup of probiotic ingredients. Amino acids, which are the building blocks of proteins, nucleobases, which form the code of DNA and RNA, and even sugars and lipids. When these objects slammed into Earth, they weren't just delivering rocks and ice. They were delivering a pre-packaged chemistry set, ready to be mixed in the planet's new warm, watery environment. The energy of the impacts themselves, along with the heat from volcanic vents on the ocean floor, could have provided the necessary spark to jump-start the reactions that linked these molecules into more complex chains. This isn't just speculation. Experiments that simulate these ancient impact conditions have successfully created amino acids and other essential organic compounds from simple ingredients. This transforms our view of these cataclysmic events from purely destructive forces into creative ones. It presents a profound duality. The same hammer that shatters the vase can also forge the steel. Without this period of intense bombardment, Earth might have remained a parched, geologically active but ultimately barren world, much like Venus is today. The late heavy bombardment essentially terraformed our planet, providing it with the two most critical components for life: vast quantities of water and the fundamental organic raw materials. It set the stage for the next great act in Earth's history, which would begin in those newly formed oceans, where those delivered molecules would eventually, and miraculously, begin to assemble themselves into the first living organisms. The scars on the moon are a silent reminder that our existence is deeply tied to a period of celestial violence that, against all odds, brought the ingredients of life to our doorstep. 66 million years ago, the reign of the dinosaurs was ended not by a rival predator or a slow decline, but by a visitor from the depths of space. An asteroid, estimated to be over 6 miles wide, screamed into Earth's atmosphere at a speed of around 45,000 miles per hour. In an instant, it struck the shallow seas near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The energy released was beyond any human scale of comparison, equivalent to billions of the nuclear bombs dropped on Hiroshima. The initial blast vaporized rock and water, sending a plume of superheated material high above the atmosphere, while shockwaves radiated outward, triggering global earthquakes and volcanic eruptions thousands of miles away. But the immediate impact was only the beginning of the nightmare. The real killer was what happened next. The colossal force of the impact hurled immense quantities of dust, soot, and sulfur aerosols high into the atmosphere, casting a shroud over the entire planet. Sunlight was blocked for years, perhaps even decades. Photosynthesis ground to a halt, causing the collapse of plant life on land and phytoplankton in the oceans, which shattered the very base of the global food web. With no sun, global temperatures plummeted, creating a long, dark, impact winter. Acid rain fell, poisoning the oceans and lakes. It's estimated that 75% of all plant and animal species were wiped out in this geological blink of an eye. The most famous victims were, of course, the non-avian dinosaurs, the mighty T. Rex, the towering Triceratops, the countless species that had dominated the planet for over 150 million years. But they were not alone. Giant marine reptiles like the mosasaurs, soaring pterosaurs, and countless species of plants and invertebrates also vanished forever. This catastrophic loss, however, created an unprecedented opportunity. The dinosaurs' dominance had kept our small, shrew-like mammalian ancestors confined to the shadows, forcing them to be nocturnal, burrowing insect eaters to avoid becoming lunch. With the dinosaurs gone and ecological niches left wide open, these surviving mammals found themselves in a new world. Without massive predators and competitors, they could finally emerge and experiment. Over the subsequent millions of years, they diversified at an explosive rate, evolving into a stunning array of new forms. Some grew large to fill the herbivore roles, others became new predators, and some took to the trees and eventually the skies. This evolutionary radiation, directly triggered by the asteroid impact, set the stage for the eventual rise of primates and, much later, humans. In a very real sense, we owe our existence to that cataclysm. If that asteroid had arrived a few minutes earlier or later, striking deep ocean instead of shallow, carbonate-rich rock that vaporized so effectively, the dinosaurs might have survived, and the world today would be a very different place. The evidence for this event is etched into the very rock of our planet. In the late 1970s, scientists Walter and Luis Alvarez discovered a thin layer of clay in rock formations all around the world, all dating to exactly 66 million years ago. This layer was incredibly enriched with the rare element iridium, which is scarce on Earth's surface but abundant in asteroids and meteors. This global iridium anomaly became the smoking gun, the definitive proof that a massive extraterrestrial object had struck the Earth at that precise moment in time, coinciding perfectly with the mass extinction event that marked the end of the Cretaceous period. This geological marker is now one of the most clearly defined boundaries in the entire fossil record, a stark, global tombstone for one era and a birth certificate for the next. This event is the ultimate demonstration of how our planet's biological destiny is intertwined with the chaotic motions of the solar system. It shows that evolution is not a steady, predictable march of progress, but a story constantly being rewritten by random cosmic accidents. A single rock from space can reset the board, ending a dynasty of giants and clearing the way for small, seemingly insignificant creatures to inherit the Earth. It's a humbling reminder that our existence is the result of both incredible fortune and unimaginable violence, a legacy written in asteroid dust and sealed by extinction. So we've seen how collisions delivered the ingredients for life, but where did those ingredients actually come from? The answer takes us from the chaotic early solar system to the very hearts of stars and the most violent explosions in the cosmos. Every single element on the periodic table, aside from the very lightest hydrogen and helium formed in the Big Bang, was created through stellar processes, and it took cataclysmic events to blast them out into the universe where they could become part of us. Think of it this way: a star is a gigantic nuclear fusion reactor. For most of its life, a star like our Sun fuses hydrogen into helium in its core, releasing the energy that makes it shine. But this is only the first step. In the cores of much more massive stars, the pressure and heat are so intense that they can force helium atoms together to form carbon, and then fuse carbon into even heavier elements like oxygen, neon, and silicon, building them up layer by layer like a cosmic onion. But there's a limit. This process of fusion actually stops at iron. Creating an iron atom doesn't release energy, it consumes it. So when a massive star's core finally becomes solid iron, the engine suddenly shuts off. Without the outward pressure from fusion, gravity wins in a fraction of a second. The star's core collapses catastrophically and then rebounds in one of the most powerful explosions in the universe, a supernova. The shockwave from this collapse blasts through the outer layers of the star, and the energy is so unimaginably vast that it forges all the elements heavier than iron in one frantic, spectacular burst. In less than a minute, elements like silver, gold, lead, and uranium are born from this incredible violence. The explosion then hurls this newly created elemental bounty out across light years of space, enriching vast clouds of gas and dust with the raw materials for new planets and life. There's another, even more extreme cosmic forge, the collision of neutron stars. When two of these incredibly dense stellar corpses, each a city-sized object with more mass than our Sun, spiral into each other and merge, the event is so energetic that it literally ripples the fabric of space-time, sending out gravitational waves we can now detect here on Earth. These collisions are thought to be the primary source for the heaviest and most precious elements in the universe, including most of the world's gold and platinum. A single neutron star merger can create and fling outward an amount of gold many times the mass of our entire planet. This means the gold in your wedding ring or a microchip was most likely born in the furious collision of two dead stars billions of years ago. These scattered elements then mix with interstellar gas, eventually becoming part of new generations of stars and planets. Our own solar system formed from just such an enriched cloud of debris, a fact confirmed by the presence of these heavy elements in everything from Earth's crust to the meteorites that occasionally fall to the surface. This is the profound connection between the cosmos and ourselves. The iron that carries oxygen in your blood, it was fused in the core of a massive star that lived and died long before our sun was born. The calcium that strengthens your bones, forged in that same stellar heart. The carbon that forms the backbone of every single organic molecule in your body. Created in the furnace of a star and then scattered by its death throes, we are not just living in the universe is literally living within us. We are walking, talking collections of ancient stardust, assembled from atoms created in the most violent and energetic events nature can produce. Our very existence is a direct consequence of these forgotten cosmic collisions, a permanent record of stellar lives and deaths written into the chemistry of our bodies. But the story of our solar system's formation isn't just about things smashing together in place. It's also a tale of incredible motion, of planets wandering far from their birthplaces. For a long time, we imagined the planets forming in a relatively orderly fashion, settling into their current orbits and staying there. But newer, more dynamic models reveal a far more dramatic history, one where the giant planets went on a monumental journey that ultimately made our existence possible. This theory is known as the Grand Tack hypothesis, and it paints a picture of Jupiter as a gravitational titan on the move, first marching inward toward the Sun before changing course and sailing back outward with Saturn in tow. This celestial dance, a gravitational tug-of-war between the planets and the disk of gas and dust surrounding the young Sun, didn't just rearrange the furniture, it completely remodeled the entire inner solar system. Imagine Jupiter, freshly formed and massive, beginning to plow through the primordial disk. Its immense gravity acts like a snowplow, gathering material and clearing a path as it slowly spirals inward toward the warmer inner regions. Left unchecked, this migration would have brought Jupiter perilously close to where the rocky planets, including Earth, were trying to form. This would have been disastrous, either gobbling up the protoplanets or hurling them into the Sun, leaving behind a barren system of asteroids. But just as Jupiter was making its way inward, Saturn finally grew large enough to exert its own significant pull. The two giants became locked in a special gravitational resonance, their orbits synchronizing. This partnership changed everything. The combined gravitational effect of the two planets began to interact with the disk in a new way, reversing the flow and pulling them both back outward like a tide turning. This tack, borrowing a term from sailing where a ship changes direction against the wind, is the heart of the model. The consequences of this grand migration were profound and twofold. First, as Jupiter moved inward and then back out, its gravity acted like a cosmic shepherd, scattering the population of asteroids and comets that filled the early system. Some of these objects, particularly water-rich asteroids from beyond the frost line, were flung inward, right into the path of the growing Earth and its rocky neighbors. This delivery service is a leading explanation for how our planet got its water. We were gifted the oceans by Jupiter's gravitational slingshot. Secondly, the Grand Tack effectively cleaned out much of the material in the inner solar system. Without this clearing action, Earth might have grown to be a much larger, uninhabitable super-Earth with a crushing atmosphere and no solid surface. Instead, we ended up with a nicely sized, rocky planet in a stable orbit within the Sun's habitable zone. This model transforms our view of giant planets from passive bystanders to active architects of planetary systems. Their gravitational influence doesn't just define their own orbits, it dictates the fate of every other world forming around them. A Jupiter-like planet that doesn't migrate, or that migrates too aggressively, can easily create a system devoid of habitable, Earth-like planets. This understanding is crucial as we look out at the thousands of exoplanets discovered around other stars. The sheer variety of systems we see, hot Jupiters orbiting recklessly close to their stars, or systems with planets in wildly eccentric orbits, can all be explained by different patterns of planetary migration. The Grand Tack shows us that our solar system's architecture, which seems so perfectly arranged for life, might be the result of a specific and fortunate series of gravitational events. It suggests that while the ingredients for life might be common in the galaxy, the planetary kitchens where those ingredients can successfully come together might be rarer and more special than we ever imagined. While the asteroids of the late heavy bombardment delivered crucial materials, another class of icy wanderers played an equally vital role in painting our world with the brushstrokes of life. Comets are not merely spectacular celestial visitors with glowing tails. They are ancient, frozen archives, pristine relics from the solar system's darkest and coldest outskirts. Often described as dirty snowballs, these objects are complex amalgamations of water ice, frozen gases like carbon dioxide and methane, dust, and rich organic compounds, all preserved in a deep freeze for over 4.5 billion years. Their very existence offers us a direct window into the conditions of the primordial solar nebula, a snapshot of the raw ingredients before they were baked into planets. Unlike asteroids, which have undergone significant heating and alteration, comets have remained largely unchanged, making them the most valuable time capsules we can study. The role of comets as delivery vehicles for water is a cornerstone of understanding Earth's habitability. The wet comets that originate from the Kuiper belt just beyond Neptune, and especially the super-icy comets from the distant Oort cloud, are composed of up to 50% water ice by mass. When one of these objects plunges toward the inner solar system and collides with a planet, the result is an immense infusion of water vapor into the atmosphere. Computational models suggest that even a relatively small number of large comet impacts during the early history of the inner planets could account for a significant percentage of their water content. For Earth, while some water was undoubtedly outgassed from volcanic activity, the isotopic fingerprint of our oceans, specifically the ratio of normal water to heavier, semi-heavy water containing deuterium, matches more closely with certain types of asteroids, but also aligns with the measurements taken of comets like the famous Hartley 2. This indicates a complex delivery service where both asteroids and comets played a part in filling our basins, with comets likely providing a crucial early supply that helped establish our planet's first hydrosphere. Perhaps even more significant than the water is the cargo of prebiotic organic matter these icy messengers carry. The notion that comets are rich in the building blocks of life moved from theory to confirmed fact with the groundbreaking Rosetta mission. For 2 years, the Rosetta spacecraft orbited comet 67P/Churyumov-Gerasimenko, and its Philae lander touched down on its surface. The data sent back was nothing short of revolutionary. The spacecraft's instruments detected a stunning array of molecules essential for life: glycine, the simplest amino acid used to build proteins, phosphorus, a key component of DNA and cell membranes, and even formaldehyde and hydrogen cyanide, which are precursor molecules that can react to form more complex sugars and amino acids. Finding these compounds on a comet billions of years old, far from the warmth of the sun, powerfully supports the idea that the fundamental chemistry for life is not a rare Earth-bound phenomenon, but a universal process that occurs in the vast molecular clouds where stars and planets are born. These comets essentially pre-pack the organic starter kit for life and distribute it throughout a young planetary system. Beyond their role in origins, cometary impacts have also acted as agents of change throughout Earth's more recent history, capable of altering the course of human civilization. While still a topic of vigorous scientific debate, a compelling hypothesis suggests that a comet fragment may have exploded in the atmosphere over North America around 12,800 years ago. This event is theorized to have contributed to the sudden onset of the Younger Dryas period, a 1,000-year-long return to Ice Age conditions. The proposed airburst would have thrown immense amounts of dust and soot into the atmosphere, blocking sunlight and causing rapid, drastic cooling. This climatic shift coincides with the extinction of megafauna like mammoths and mastodons, and significant changes in the patterns of early human hunter-gatherer societies. Whether from a direct hit or an atmospheric explosion, the event illustrates that comets are not just relics of the deep past. They remain part of the solar system's active dynamics, capable of influencing climate and ecology on a global scale even after life has become established. This dual identity, as both bringers of life's ingredients and potential disruptors of its progress, makes comets some of the most fascinating and consequential objects in our cosmic neighborhood. Nestled between the orbits of Mars and Jupiter lies a vast, sprawling ring of cosmic debris, the asteroid belt. It's easy to picture this region as a chaotic, densely packed junkyard, just like we see in science fiction films, but the reality is far more fascinating and less congested. If you were to fly a spacecraft through the main belt, you'd find it is overwhelmingly empty space, with millions of rocky bodies separated by vast distances. This isn't just a random assortment of space rocks. It's a fossilized construction site, a relic from the solar system's violent birth that never got to finish its job. 4.5 billion years ago, this was the construction zone for a potential planet, a world that never was. The tremendous gravitational influence of the nearby giant Jupiter acted like a constant, disruptive force, stirring up the material with such ferocity that the particles could never peacefully coalesce into a single planetary body. Instead of forming a planet, these fragments were left as permanent clues to our origins, each asteroid a time capsule holding pristine material from the very dawn of our solar system. This vast reservoir of ancient rock doesn't just sit idly in its orbit. It functions as a dynamic cosmic shooting gallery. The gravitational nudges from Jupiter and occasional interactions with Mars are enough to perturb the orbits of some of these asteroids, sending them on new paths that can cross the orbital lanes of the inner planets, including our own. This process is how near-Earth objects are born. These wayward asteroids become the projectiles in a celestial game of chance, with Earth as a moving target. Throughout history, these impacts have been the great architects and destroyers of our world. They've delivered the water and organics that made life possible, but they've also delivered extinction-level events, like the one that ended the reign of the dinosaurs. Every single crater on our moon and on Earth's weathered surface is a stark reminder that this process is not a thing of the distant past. It is an ongoing feature of our solar system's dynamics. Yet within this apparent threat lies incredible opportunity. These asteroids are not all simple lumps of rock. They are diverse worlds in their own right, each with a unique composition telling a different chapter of the solar system's story. Some, known as carbonaceous asteroids, are dark, primitive bodies rich in water, clay minerals, and complex organic compounds, the very same materials that likely seeded early Earth. Others, the metallic asteroids, are the shattered cores of ancient protoplanets that were broken apart in long-ago collisions. These wandering mountains of iron, nickel, cobalt, and platinum group metals represent resources almost beyond valuation. The prospect of asteroid mining moves from science fiction to a tangible, though complex, future industry. A single metallic asteroid could contain more platinum than has ever been mined in all of human history, potentially revolutionizing technology and clean energy. The water ice trapped within other asteroids could be split into hydrogen and oxygen to create rocket fuel, effectively turning these bodies into cosmic gas stations for deep space exploration, enabling longer missions to Mars and beyond. This dual nature, both grave threat and incredible treasure, forces us to look at the asteroid belt in a new light. It is a place of both peril and promise. The same gravitational mechanics that send a city killer toward Earth could also one day guide a mining robot toward a trillion-dollar payload. Our future in space may depend on our ability to navigate this dichotomy, to develop the technology not only to deflect a dangerous asteroid, but also to harness the incredible resources they offer. The continued existence of the asteroid belt is a powerful reminder that our solar system is not a static museum piece. It is a living, breathing, and still evolving system, where the gentle drift of a rock over millions of years can set in motion events that either end worlds or help a civilization begin its journey to the stars. We have journeyed from the violent impacts that shaped our solar system to the stellar furnaces that forged the elements of life. But to witness the ultimate expression of cosmic collisions, we must pull our perspective far back, to a scale that truly defies human comprehension. We are no longer talking about rocks hitting planets or even stars exploding. We are talking about the grandest structures in the universe themselves, galaxies. These immense islands of stars, gas, and dark matter, each containing hundreds of billions of suns, are not static. They move through the cosmic void, and sometimes their paths are destined to cross in the most spectacular of dances. Our own Milky Way galaxy and our nearest large galactic neighbor, Andromeda, are currently hurtling towards each other at a breathtaking speed of about 250,000 miles per hour. In roughly 4.5 billion years, these two titans will begin a gravitational tango that will last for billions more, ultimately merging into a single, new galaxy that astronomers have already nicknamed Milky. To our brief human lifespans, this process seems like the slowest of slow-motion events, but in cosmic time, it is a fundamental and recurring engine of change. When two galaxies meet, they don't crash in a fiery explosion of stars colliding head-on. The distances between stars are so vast that actual stellar impacts are incredibly rare. Instead, the galaxies pass through one another, their gravitational fields acting like immense, invisible hands that knead and distort their shapes, pulling out long, streaming tails of stars and gas in spectacular arcs. It is this gravitational chaos that becomes a catalyst for breathtaking creation. The immense clouds of gas and dust within each galaxy are violently compressed and shaken, triggering furious waves of new star formation. These starburst regions, as they are called, light up the merging galaxies, creating brilliant blue clusters of hot, young stars at a rate hundreds of times faster than in a quiet galaxy like our Milky Way is today. This creative frenzy has a profound purpose. All those new, massive stars live fast and die young, exploding as supernovae and flooding the galactic environment with the heavy elements forged in their cores. A galactic merger, therefore, is not just a rearrangement of existing stars. It is a factory for the very materials that build rocky planets and life. It enriches the galactic soup with the iron, oxygen, carbon, and silicon necessary for future generations of stars and planets. Furthermore, the gravitational turbulence can fling individual stars and even entire planetary systems out of the galactic disk entirely, hurling them into the lonely darkness of intergalactic space. Imagine a star with its retinue of planets, ejected from its galactic home to wander the void between galaxies forever. While this might seem like a terrifying fate, it also suggests that life, if it exists out there, could potentially survive in the most isolated of environments, completely untethered from a host galaxy. The legacy of these colossal mergers is written across the sky. Most of the large galaxies we see today, including our own Milky Way, are likely the products of such ancient collisions, having grown to their current size by consuming smaller dwarf galaxies. The smooth, featureless ellipses of giant elliptical galaxies are thought to be the final products of massive mergers, their gas used up in a final burst of star formation, leaving behind a population of older stars. This cycle of galactic interaction, from delicate gravitational dances to full-scale mergers, is a primary driver of cosmic evolution. It ensures that the universe is not a static museum, but a dynamic, ever-changing arena where destruction and creation are inextricably linked on the most epic of scales. The eventual merger of the Milky Way and Andromeda is not an end. It is a transformation, a necessary step in the life cycle of galaxies that will ultimately create a new, more massive galaxy, seeding it with the enriched materials for new worlds and perhaps new possibilities for life billions of years from now. But this brings us to one of the most fundamental and beautiful questions about our planet. Where did all this water actually come from? The sight of our vast, blue oceans from space is so iconic. It's easy to assume that water was just always part of Earth's original recipe. But the truth is far more fascinating and points directly to our planet's violent, cosmic beginnings. The early Earth formed hot and dry in the inner solar system, a region where the sun's fierce energy made it impossible for water ice to condense and stick around. So if water couldn't form here naturally, it had to be delivered. For decades, scientists have been piecing together this incredible delivery story, and the evidence points to two main sources. A small amount was sweat out from the planet's own interior through billions of years of volcanic activity, a process called outgassing. But the vast majority, the water that fills our ocean basins, likely arrived on board icy asteroids and comets that pummeled the young planet during the late heavy bombardment. This isn't just a wild guess, it's a theory backed by some brilliant cosmic detective work, specifically through the science of isotopic analysis. Think of it like this: not all water is identical. A tiny fraction of water molecules are slightly heavier because they contain deuterium, a heavier form of hydrogen. By measuring the ratio of normal water to this heavier, semi-heavy water, scientists can get a kind of chemical fingerprint. They can then compare the fingerprint of Earth's oceans to the fingerprints of different types of comets and asteroids. Early measurements of comets from the distant Oort cloud showed a deuterium ratio that was much too high, which initially seemed to rule them out as our primary water source. But then, missions like the European Space Agency's Rosetta spacecraft, which visited Comet 67P, found that a different class of comets, those from the closer in Kuiper belt, had a deuterium ratio that was a much closer match. Meanwhile, studies of certain water-rich asteroids called carbonaceous chondrites revealed a deuterium ratio that is virtually a perfect match for Earth's water. This tells us that our oceans were likely painted by a mixed palette of cosmic impacts. A steady rain of asteroids from the outer asteroid belt probably provided the bulk of the delivery, with a significant contribution from Kuiper belt comets that were nudged inward by the gravitational influence of the giant planets. Each impact was a violent event, but in the chaos, the ice within these objects would vaporize and then eventually condense to fall as rain over millions of years, slowly filling the lowest points on the planet's surface to create the first primitive oceans. Without this celestial rain service, Earth might have remained a dry, barren world much like Venus. a planet tragically locked in a runaway greenhouse effect with no oceans to regulate its climate or serve as a cradle for life. The water that allows for every biological process on our planet, from the simplest chemical reaction to the most complex ecosystem, is a gift from the cosmos, a souvenir from the frozen outer reaches of our solar system. This extraterrestrial origin story for Earth's water completely reshapes how we search for life beyond our world. It implies that the ingredients for habitable planets are not rare or unique to our solar system. The processes that built our system, the formation of gas giants, the migration of planets, the scattering of icy bodies inward, are likely common around other stars. If water is a standard delivery item for rocky planets forming within the habitable zone of their star, then oceans could be a frequent feature across the galaxy. This expands the potential for life immensely. We're no longer just looking for Earth twins. We can now consider icy moons like Jupiter's Europa or Saturn's Enceladus, which have vast subsurface oceans sealed beneath icy crusts, as prime candidates. Their water almost certainly originated from the same primordial population of icy impactors. The mystery of Earth's water connects us directly to the broader workings of the universe, suggesting that the same cosmic processes that made our world blue could be doing the very same thing right now around countless other stars, painting other worlds in the beautiful, life-giving color of water. While the asteroid that ended the age of dinosaurs presents the most dramatic example of climate disruption, it is far from the only one. Throughout Earth's deep history, major cosmic impacts have repeatedly acted as powerful, if brutal, climate regulators, their effects rippling across the globe for years or even decades after the initial collision. The mechanism is both terrifying and elegantly simple. When a large object strikes the planet, it blasts immense quantities of dust, soot, and sulfur-rich aerosols high into the stratosphere. Unlike weather, which occurs in the lower atmosphere, this fine particulate haze can encircle the entire planet, forming a persistent shield that reflects a significant portion of incoming sunlight back into space. The result is a rapid and profound global cooling, a phenomenon known as an impact winter. Sunlight is dimmed, photosynthesis grinds to a halt, and temperatures plummet, creating a chain reaction that can collapse ecosystems and trigger mass extinctions. These ancient events are more than just historical footnotes. They serve as stark, natural experiments that allow scientists to model and understand how particulate matter influences our climate system on a grand scale. This understanding provides a crucial, albeit unsettling, parallel to human-caused climate change and even to potential solutions. The same principles of atmospheric physics that govern the dinosaur-killing impact winter are directly applicable to modern geoengineering proposals, specifically the concept of solar radiation management. One theoretical idea involves deliberately injecting reflective sulfate particles into the stratosphere to mimic the cooling effect of a major volcanic eruption, thereby offsetting some of the warming caused by greenhouse gases. By studying the long-term climatic aftermath of cosmic impacts, scientists can better predict the potential efficacy, unintended consequences, and risks of such a drastic intervention. Would it cause drastic shifts in global rainfall patterns, leading to droughts in some regions and floods in others? Could it damage the ozone layer? The geological record of impact winters offers a valuable, real-world dataset to help answer these critical questions, providing a cautionary backdrop to one of the most controversial debates in climate science. To see a more recent example of this phenomenon at work, we need only look to the year 1815 and the catastrophic eruption of Mount Tambora in Indonesia. While not a cosmic impact, this volcanic event produced impact-like effects on a global scale, offering a sobering case study from human history. the eruption was the most powerful in recorded history, ejecting so much ash and sulfur dioxide into the stratosphere that it significantly reduced the amount of sunlight reaching the Earth's surface. The very next year, 1816, became known across the Northern Hemisphere as the Year Without a Summer, or 1800, and froze to death. New England saw snowfalls in June, crops failed spectacularly across Europe and North America, and famine and disease followed closely behind. The societal disruption was immense, triggering food riots, mass migrations, and even inspiring a period of profound creativity. The gloomy weather famously forced a vacationing Mary Shelley and her friends to stay indoors, leading them to a ghost story contest that produced the novel Frankenstein. The lesson from Tambora is crystal clear. Sudden, large-scale injections of particles into the upper atmosphere can have immediate and devastating consequences for human civilization, overriding all other climatic factors. It demonstrates with terrifying clarity how our agricultural systems, economies, and social structures are exquisitely vulnerable to abrupt changes in the climate, whether the cause is a volcano, a potential future impact, or even a poorly conceived geoengineering project. By examining these historical parallels, we gain more than just academic knowledge. We acquire a vital framework for preparedness. Understanding how the climate system responds to extreme forcing events helps us improve models for future climate scenarios, develop more resilient food systems, and ultimately underscores the profound responsibility we hold in managing the delicate atmospheric balance that makes our world habitable. The scars of past cosmic and volcanic violence teach us that our climate is not an immutable constant, but a dynamic and sometimes fragile system, one that we are only now beginning to influence and must strive to protect. Far beyond the orbit of Neptune, in the cold, silent outskirts of our solar system, lie two of the most mysterious and ancient regions known to science, the Kuiper belt and the Oort cloud. Think of them not as empty space, but as vast, deep freeze archives, preserving pristine material from the very dawn of our planetary system over 4.5 billion years ago. The Kuiper belt is a vast donut-shaped ring of icy bodies, a realm where dwarf planets like Pluto, Haumea, and Makemake reside as frozen royalty. This isn't some distant abstraction. It's a real place we've now visited, thanks to the intrepid New Horizons spacecraft, which gave us our first breathtaking close-up of Pluto's heart-shaped glacier and its complex mountainous terrain. But the Kuiper belt is just the inner vault of this cosmic library, extending outward for a staggering distance, perhaps as far as a light year into the void, is the Oort cloud, a theoretical spherical shell of trillions of icy objects so distant that they are only loosely bound by the sun's gravity, forming a fragile bubble at the very edge of the sun's influence. These regions are not static museums, they are dynamic reservoirs that have played, and continue to play, a crucial role in Earth's story. The icy denizens of these zones are the ultimate time capsules. Locked within their frozen interiors are unchanged samples of the original gas, dust, and ice that swirled in the protoplanetary disk from which our solar system formed. When the orbits of these objects are perturbed, perhaps by the gravitational nudge of a passing star, the gentle tidal pull of the Milky Way galaxy itself, or a collision within the cloud, they can be sent on a long, falling journey inward toward the sun. As they approach the heat of our star, they transform into the comets we see streaking across our skies, their brilliant tails a visible testament to this delivery mechanism. This process is not a relic of the distant past, it is an ongoing cycle. Throughout Earth's history, comets from these distant reservoirs have likely been a continuous, if sporadic, source of delivery, bringing not just water ice but also complex organic molecules to our planet. This means the same process that seeded early Earth with the ingredients for life may still be subtly at work today. And while the probability is low, the possibility remains that a future disturbance could send another large object on a collision course with Earth, a reminder that the solar system is an active and sometimes dangerous place. This is precisely why missions like New Horizons are so revolutionary. By visiting a Kuiper belt object up close, the spacecraft's flyby of Arakoth revealed a stunning, untouched binary object that looks like two pancakes stuck together. We are essentially conducting a geological dig into the past without ever leaving the solar system. Its pristine, unaltered shape tells us that these objects really have been sitting there, unchanged, since the very beginning, confirming that these distant regions are indeed the frozen archives we theorized. Every byte of data returned helps us decode the original conditions and composition of the building blocks that eventually formed planets like Earth, directly informing our understanding of how we came to be. The existence of the Oort cloud and Kuiper belt fundamentally changes our perspective on the solar system's scale. Our home is not just the 8 planets we learned about in school. It is a vast sphere of influence whose tendrils reach halfway to the next star. These distant, frozen realms remind us that our planetary system is not an isolated island, but is connected to the wider galaxy, occasionally exchanging material with the interstellar medium. They are the ultimate reminder that the story of our existence is written not just on Earth, but in the most remote and frozen corners of our celestial neighborhood, waiting for us to decipher its secrets. But the story of cosmic collisions goes far beyond what they deliver to a planet's surface. They also reach deep into its very heart, engineering the internal conditions that can make or break its potential for life. When 2 planetary bodies slam together, the energy released is so immense that it doesn't just create craters, it can fundamentally reshape the planet's core. Imagine the force required to melt rock and vaporize metal. That same cataclysmic energy can turn the solid iron heart of a world into a churning, molten ocean. This liquefied, spinning metal core is the engine room for one of a planet's most vital features, its global magnetic field. Through a process called dynamo action, the convective motion of this molten iron, combined with the planet's rotation, generates powerful electrical currents that create a protective magnetic bubble around the entire world. This isn't a static shield, it's a dynamic, living force field born from motion and chaos. Our own Earth is the prime example of this miraculous protection. While our magnetic field is generated by the ongoing churning of liquid iron in the outer core, many scientists theorize that its strength and stability may have been critically influenced by the planetary collisions of our youth. The colossal impact with Thea that gave us the Moon, for instance, would have delivered an unimaginable amount of energy directly into Earth's interior. This could have completely remixed our core, supercharging the dynamo and setting the stage for the robust magnetic field we enjoy today. This invisible shield is our planet's first line of defense against the solar wind, a constant stream of high-energy particles blasted outward from the sun. Our magnetic field deflects this relentless assault, funneling charged particles harmlessly toward the poles to create the beautiful auroras, while safeguarding our atmosphere and surface from being stripped away and sterilized. To understand the life-giving importance of this magnetic shield, we need only look to our neighboring planet, Mars. The red planet presents a tragic, silent lesson in what happens when this protective field fails. Billions of years ago, Mars was a much more Earth-like world. Evidence from rovers and orbiters shows it had vast oceans, flowing rivers, and a thick atmosphere that could have supported life. But Mars is a smaller planet, and its core cooled and solidified relatively quickly. Without a molten, churning interior to power a strong magnetic dynamo, its global field faded away. Once defenseless, Mars's atmosphere was exposed to the full fury of the solar wind, which, over hundreds of millions of years, systematically stripped it away into space. The water on the surface, no longer protected by atmospheric pressure, either evaporated or froze deep underground, leaving behind the cold, barren desert world we see today. The fate of Mars starkly illustrates that having the right ingredients for life, water and organics delivered by impacts, is not enough. A planet must also have the internal engine to protect those gifts, and that engine is often forged or fine-tuned by the very violence that delivered them in the first place. This profound connection reveals a deeper layer of cosmic fine-tuning. It's not just about a planet being in the so-called Goldilocks zone, the right distance from its star for liquid water to exist. It's also about the planet's internal Goldilocks conditions, a core that remains molten for billions of years, spinning at just the right rate to generate a sustained magnetic dynamo. Giant impacts can be the random, violent events that kick-start or reset this process, turning a potentially habitable world into a truly living one. They are the universe's way of not just supplying the materials for life, but also installing the planetary security system that keeps those materials safe. In this way, the physics of colossal collisions and the fate of living worlds are inextricably intertwined, a reminder that our existence depends on a chain of events that reached from the chaos of the early solar system right down to the molten iron heart of our planet. Now we arrive at one of the most subtle and profound mysteries in the story of life's origins, a puzzle written not in the grand scale of craters or extinction events, but in the very shape of the molecules that make up every living thing. If you could shrink down to the molecular level and look at the building blocks of life like amino acids, you'd discover something strange. Many of these molecules are what chemists call chiral, meaning they come in two forms that are perfect mirror images of each other, just like your left and right hand. You can't superimpose one on the other, they are distinct, a property known as handedness, and here is the mystery. Life on Earth, in all its incredible diversity, uses only one of these forms. Our proteins are built exclusively from left-handed amino acids, and our DNA and RNA use only right-handed sugars. This universal preference is known as homochirality, and it is absolutely essential. If a right-handed amino acid accidentally gets incorporated into a protein built for left-handed ones, the entire structure can fail to function. So how did life, in its very first steps, make this exclusive choice? How did randomness give way to such a specific, universal order? The answer may once again lie in the violence of our cosmic beginnings. One compelling theory points to the heavens, to the most energetic events in the universe. When neutron stars collide, they do more than just create gold. They also unleash tremendous bursts of radiation, including circularly polarized light. This is a special kind of light that twists as it travels through space, and it has a fascinating property. It can selectively destroy one mirror image form of a molecule over the other. As this polarized light from a distant stellar catastrophe traveled through vast molecular clouds in space, where amino acids were already forming on ice-covered dust grains, it could have slowly but surely broken down more of one hand than the other, creating a slight excess, a small bias, in the molecular building blocks before they ever reached a planet like Earth. This tiny initial nudge from a cosmic event could have been the first step, setting the table for life's exclusive preference, but the cosmos may have provided a second, more local mechanism right here on the early Earth. The same impacts that delivered water and organics could also have provided the energy and conditions to enforce this handedness. Scientists have recreated the violent conditions of these collisions in the lab. By simulating the immense shock waves of a comet or asteroid impact, and firing projectiles into ice mixtures containing simple precursor molecules. They have not only successfully created amino acids, they have found that these lab-synthesized amino acids often show a slight but significant bias towards one hand. The sheer force and energy of the impact itself, it seems, can provide the necessary push to break the symmetry and favor one form over the other. It's a stunning connection. The same catastrophic events that could sterilize a planet might also, paradoxically, provide the key to organizing the chemistry that leads to life. This moves us from a story of pure, undirected randomness to one where chaos itself can be a guiding force. The ferocious energy of cosmic violence introduces a bias, a breaking of the mirror that tips the scales. From that initial slight imbalance, the process of life's emergence could then amplify the effect. Perhaps the slightly more abundant left-handed amino acids began forming more stable or efficient chains, outcompeting their mirror image cousins and eventually becoming the standard. This concept connects the unimaginable power of colliding neutron stars and asteroid impacts to the most delicate and precise processes of biochemistry. It suggests that the path from non-life to life wasn't a gentle, gradual process, but was instead catalyzed by the most extreme events the universe has to offer. The fundamental asymmetry of life, a requirement for the complex interactions that make biology possible, might be a direct signature of our violent cosmic heritage, a permanent reminder that our existence is the product of both incredible chance and the universe's own brutal creative forces. Yet this cosmic legacy of creation comes with a sobering caveat: the very same processes that gifted us life hold the potential to take it all away. The solar system remains a dynamic shooting gallery, with countless asteroids and comets still tracing orbits that intersect our own. Consider Bennu, a carbon-rich asteroid roughly the height of the Empire State Building, which has a small but real probability, about 1 in 2,700, of colliding with Earth in the late 21st century. While those odds are low, the consequences of an impact from an object of that size would be globally catastrophic, releasing energy equivalent to thousands of nuclear bombs and potentially altering the climate for years. Bennu is not alone. It is one of thousands of known near-Earth objects, and many more remain undetected, hidden in the glare of the sun or lurking in the vast darkness of space. The challenge we face is not one of mere curiosity, but of planetary-scale risk management, a race against time to identify and characterize these celestial threats before one of them has our name on it. The good news is that humanity is no longer a passive spectator in this cosmic drama. In a landmark demonstration of planetary defense, NASA's a double asteroid redirection test, or DART mission, successfully proved that we can actively alter the course of an asteroid. The spacecraft was deliberately crashed into a small moonlet called Dimorphos, which orbits a larger asteroid named Didymos. The impact was not meant to destroy the object but to nudge it, to change its orbital period through the transfer of kinetic energy. The result was a resounding success. Dimorphos's orbit was shortened by 32 minutes, far exceeding initial predictions and demonstrating that kinetic impactor technology is a viable method for deflecting a hazardous asteroid, provided we have enough advance warning. This mission represents a monumental leap from theoretical concept to proven capability, transforming planetary defense from science fiction into tangible reality. However, a single successful test does not mean our work is done. The first and most critical step in planetary defense is finding the threats. Our current catalogs are incomplete, with an estimated 40% of near-Earth objects larger than 140 meters still undiscovered. These are the city killers, objects large enough to cause regional devastation, and we simply do not know where they all are. initiatives like the upcoming Surveyor Space Telescope are designed to address this gap. This infrared observatory will be positioned in space to peer into regions of the sky that are difficult to observe from Earth, dramatically accelerating the rate at which we discover and track potentially hazardous objects. Filling these catalogs is our highest priority, as it provides the essential early warning that is the foundation of any defense strategy. Knowing an asteroid is coming is only half the battle. The other half is knowing what to do about it. Deflection techniques vary depending on the size of the object, its composition, and how much lead time we have. For a small asteroid with decades of warning, a gentle, sustained push might be sufficient. One proposed concept is a gravity tractor, a spacecraft that would fly alongside the asteroid for years, using its own tiny gravitational pull to slowly tug the object into a safer orbit. For larger asteroids or shorter timelines, a more forceful kinetic impactor like the DART mission might be required. In the most extreme scenarios, some scientists have theorized about using a nuclear explosive device to vaporize a portion of the asteroid's surface, creating a jet of material that acts like a rocket thruster to push it off course. Each method has its own complexities and requires extensive research and preparation long before a threat is identified. This leads to perhaps the most complex challenge of all: international coordination and decision-making. An asteroid threat is a global problem that demands a global solution. Who has the authority to decide to deflect an asteroid? The process of altering its trajectory, while intended to save the planet, could inadvertently shift the impact point from one uninhabited region to a populated one. This creates a profound ethical and geopolitical dilemma. A robust planetary defense strategy requires unprecedented international cooperation with clear protocols, transparent data sharing, and agreed-upon frameworks for action. Organizations like the United Nations Office for Outer Space Affairs are already working on these very issues, fostering dialogue to ensure that when a threat is identified, the world can respond not as a collection of individual nations, but as a united humanity with a shared goal of survival. The endeavor to protect Earth from cosmic impacts is a powerful testament to how far we have come as a species. We have evolved from organisms shaped by ancient collisions to a civilization capable of understanding those forces and taking steps to defy them. This mission uniquely blends cutting-edge science and technology with profound existential questions, connecting our deepest past to our long-term future. It is a practical imperative born from our understanding of cosmic history, a direct application of knowledge that transforms us from potential victims of celestial chance into active guardians of our world. The same vigilance that allows us to appreciate the violent beauty of our origins now empowers us to secure our destiny. For centuries, our solar system was the only one we knew, a seemingly unique blueprint for how planets form and evolve. But with the discovery of thousands of exoplanets, we've been granted a front-row seat to a cosmic laboratory, allowing us to witness the processes that built our own world unfolding in real time around other stars. One of the most compelling pieces of evidence we see is the presence of vast, swirling disks of dust and debris encircling young stars. These aren't just featureless clouds. They are the unmistakable signposts of ongoing construction and, more importantly, demolition. This dust doesn't just appear, it's constantly being replenished by the grinding and smashing of countless planetesimals, asteroids, and protoplanets, a continuous cycle of collisions that mirrors the chaotic early days of our own solar system. By studying the structure and composition of these disks, astronomers can essentially watch planetary formation in action, confirming that the violent processes we believe shaped our past are not unique to us, but are a universal phase in the life of a star system. A stunning example of this can be found right in our celestial backyard around the brilliant young star Fomalhaut, located just 25 light-years away. Hubble Space Telescope images revealed a breathtakingly sharp, brilliant ring of debris surrounding the star, often described as the Eye of Sauron for its dramatic appearance. This ring isn't a peaceful collection of static rocks. It's a dynamic, violent arena. The very existence of such a narrow, well-defined belt implies that it is being gravitationally sculpted and confined by unseen planets, much like Jupiter shepherds our own asteroid belt. But more crucially, the dust that makes the ring so bright and visible is thought to be the pulverized remains of constant, shattering collisions between icy bodies within the ring itself. Fomalhaut's disk is a snapshot of a solar system in its turbulent youth, a living museum exhibit demonstrating the relentless bombardment that once filled our own skies. The detective work goes even deeper when we examine the planets themselves. Some exoplanets show bizarre and extreme characteristics that defy simple explanation until we apply the lessons from our own cosmic collisions. Astronomers have discovered worlds like Kepler 107c, a planet with an unexpectedly high density, suggesting it might be the dense, iron-rich core of a much larger planet that had its outer rocky mantle violently stripped away in a giant impact. Then there are systems where planets show wild, highly elliptical orbits, a telltale sign of a dynamically unstable past where gravitational interactions likely flung planets into each other or out of the system entirely. Perhaps most intriguing are the exoplanets we've found that seem to be missing their atmospheres entirely. One leading theory is that these worlds were victims of catastrophic collisions early in their history, impacts so powerful that they literally blew away the primordial gases that enveloped them, leaving behind barren, airless cores. These are the exoplanetary equivalents of the moon-forming impact that shaped our Earth, suggesting that such planet-altering violence is a common, if not expected, part of a solar system's growing pains. All of this evidence coalesces into a single, profound question. Is Earth's history special, or is it the cosmic standard? The answer, it seems, is leaning heavily toward the latter. The prevalence of dusty debris disks and the telltale scars on exoplanets strongly suggest that the delivery of water and organics via impacts, the planetary migration that rearranges systems, and the giant collisions that reset a world's fate are not rare anomalies. They appear to be fundamental, universal mechanisms. This doesn't just inform our search for habitable worlds, it supercharges it. If the processes that made Earth a living world are common, then the ingredients for life are likely scattered throughout the galaxy. A rocky planet forming within its star's habitable zone has a statistically high chance of being bombarded by water-rich comets and organic-laden asteroids, just as Earth was. It might experience a planetary migration that places it in a stable orbit, and it might even suffer a colossal impact that tilts its axis to create seasons, and perhaps even creates a large moon to stabilize its climate. The story of our existence, written in violence and chaos, might be the universe's most common recipe for life. This deep-seated, almost primal awareness of celestial danger is not confined to the ancient world. It pulses through the very heart of modern storytelling. Our cinemas are regularly filled with blockbuster spectacles that explore the theme of planetary impact, from the sobering realism of films like Deep Impact to the more fantastical heroics of Armageddon. These narratives are more than just entertainment. They are a form of cultural rehearsal, a way for us to collectively grapple with an existential threat from the cosmos in the safety of a darkened theater. They allow us to ask the terrifying question, what would we do? And to explore the full spectrum of human response, from panic and despair to ingenuity and courage. This genre persists because it taps into a fundamental and shared vulnerability, a recognition that our technological mastery of the planet does not exempt us from the random violence of the universe. It is a modern-day mythology, complete with its own heroes, prophecies, and apocalyptic visions, serving the same psychological purpose as the legends of old, to help us process the unthinkable. This cultural engagement reveals a profound duality in the human psyche. On one hand, these stories are born from a place of deep fear, the fear of annihilation, of powerlessness, of our fragile civilization being snuffed out by an indifferent rock from the void. Yet, on the other hand, they are also expressions of incredible hope and resilience. We are fascinated by these scenarios not just because we are afraid of them, but because we are also drawn to the challenge they represent. They test our species' capacity for cooperation, our ability to triumph over seemingly insurmountable odds using reason, science, and collective will. The very act of telling these stories is an act of defiance against the chaos of the cosmos. It is our way of asserting that even in the face of ultimate forces, we will strive, we will fight, and we will seek to understand. This narrative tradition is a vital part of our psychological toolkit, helping to build a form of cultural resilience and preparing us, on some level, to confront a future where such a threat might become real. By tracing this thread from ancient myth to modern cinema, we see that our relationship with the cosmos is far more intimate and complex than simple observation. The same cosmic collisions that literally sculpted our planet and guided our evolution have also carved deep channels in our collective consciousness. They have influenced our art, our religion, our stories, and our deepest fears. This reveals that we are not merely inhabitants of the universe looking out at a distant, external reality. We are the universe itself, become self-aware, looking back at its own violent and creative history and trying to find meaning within it. Our cultural narratives about cosmic violence are a fundamental part of how we perceive our place in the grand scheme of things, not as masters of creation, but as conscious participants in an ongoing, dynamic, and sometimes dangerous cosmic story. These stories are the legacy written not in rock, but in the human spirit, a permanent record of our awe and our apprehension under the same stars that both create and destroy. The pursuit of understanding cosmic violence has yielded a treasure trove of unexpected and profoundly practical benefits here on Earth, spinning off technologies that protect us, connect us, and fuel our modern world. It turns out that preparing for the ultimate catastrophe of an asteroid impact requires pushing the boundaries of science and engineering in ways that solve much more immediate human challenges. This research, born from a desire to comprehend our cosmic past and secure our future, has become a powerful engine for innovation, delivering tangible improvements to our daily safety and prosperity. Consider the field of material science, where the extreme conditions of a hypervelocity impact have become a laboratory for creating stronger, more resilient substances. To understand what happens when a rock traveling 20 times faster than a bullet slams into a spacecraft hull or a planetary surface, scientists use advanced facilities like light gas guns and laser-driven projectile launchers. These experiments have provided crucial data that is directly applied to designing better protective systems for our society. The same principles used to model the integrity of a spacecraft shield against micrometeoroid strikes are now used to develop next-generation body armor for soldiers and law enforcement, creating lighter, more flexible materials that can dissipate incredible amounts of energy. The advanced ceramics and layered composite alloys born from this research don't just defend against space debris, they save lives on the battlefield and in dangerous professions every single day. The urgent need to find and track potentially hazardous asteroids has catalyzed a revolution in our ability to observe the sky with unparalleled precision and sensitivity. Programs like NASA's Planetary Defense Coordination Office have funded the development of cutting-edge radar systems and wide-field survey telescopes specifically designed to detect faint, fast-moving objects against the backdrop of stars. The algorithms created to identify a single pixel of light moving in a predictable path across a series of images have found powerful applications right here on Earth. This sophisticated software is now used in aviation radar systems to track aircraft with greater accuracy and to monitor for drones in restricted airspace. The technology also excels at terrestrial disaster monitoring, where it can be trained to spot the faint infrared signature of a nascent wildfire long before it erupts into an uncontrollable inferno, or to track the movement of landslides and volcanic ash plumes, providing early warnings that save lives and property. Even the ancient scars of impacts, the craters that dot our planet's surface, have become guides to untold mineral wealth, turning sites of past destruction into engines of modern economic opportunity. The immense energy of a cosmic collision creates unique geological conditions that can concentrate rare and valuable elements. The Sudbury Basin in Ontario, Canada, one of the world's largest and oldest impact structures, is a phenomenal example. The cataclysm that formed it nearly 2 billion years ago fused the local rock with metals from the impacting asteroid itself, creating one of the planet's richest deposits of nickel, copper, and platinum group elements. This single crater has been a cornerstone of North American mining for over a century. Similarly, the subterranean structures of impact craters can create perfect geological traps for fossil fuels. The porous, fractured rock beneath the crater can form reservoirs where oil and natural gas accumulate, making these ancient wounds valuable targets for energy exploration. By learning to read the subtle signs of an impact structure, geologists can literally follow the path of destruction to discover the resources that power our civilization. This beautiful synergy between the cosmic and the commonplace demonstrates that knowledge is never confined to a single domain. The drive to answer profound questions about our origins and to guard against existential threats consistently delivers down-to-earth solutions that make our world safer, more connected, and more prosperous. The radar that scans the heavens for asteroids also watches over our forests for fire. The material designed to shield a probe from space dust also protects a first responder from harm. The map that charts an ancient crater also guides us to the materials that build our future. Our investment in understanding the violent cosmos is an investment in ourselves, paying dividends that ripple through every facet of our technological society, and proving that the quest to touch the stars always leaves us with a better grasp on our own world. But how do we know all of this? How can we be so certain about events that happened millions or even billions of years ago? The evidence isn't just in the stars or on the moon. It's written here on Earth if you know where to look. Our planet's surface is a vast, open book of cosmic history, and impact craters are its most dramatic chapters. Over 200 of these scars have been officially identified across every continent, from the 2-billion-year-old, deeply eroded vastness of the Vredefort Dome in South Africa to the terrifyingly recent Chelyabinsk airburst over Russia in 2013 that injured over 1,000 people with its shockwave. Each one is a crime scene, and scientists are the detectives, using a fascinating toolkit of geological evidence to piece together what happened. The first piece of undeniable evidence is something called shocked quartz. Ordinary quartz, one of the most common minerals on Earth, has a very specific crystalline structure, but when a massive shock wave from a hypervelocity impact passes through it, the structure is permanently altered, creating lamellary, fine, parallel lines of deformation that can only be formed under pressures far greater than anything even the most violent volcanic eruption can produce. Finding shocked quartz in a layer of rock is like finding a bullet casing at a shooting. It's the smoking gun for an extraterrestrial impact. Then there are tektites. These are beautiful, often olive green or black, glassy objects formed when the immense heat of an impact melts the target rock and hurls it high into the atmosphere, where it solidifies into aerodynamic shapes before raining down hundreds of miles away. Finding a field of these glassy droplets allows scientists to trace the fallout pattern and even estimate the size and direction of the impactor. Beyond these, geologists also look for shatter cones, conical, striated rock formations that point back toward the source of the shockwave, and layers of sediment rich in iridium, that rare element we discussed that is far more common in asteroids than in the Earth's crust. This detective work does more than just confirm that a rock fell from the sky. It allows us to accurately date these cataclysmic events, tying them directly to the story of life on Earth. By examining the geological layers or strata in which these impact markers are found, scientists can correlate the collision with known periods of mass extinction or dramatic climate shift. The most famous example is the KPG boundary layer, that thin, global line of clay enriched with iridium and soot that marks the end of the dinosaurs. But there are others. The Sudbury Basin in Canada, one of the largest and oldest known impact structures, is now believed to be linked to a significant dip in global oxygen levels around 1.8 billion years ago. By mapping these events in time, we are essentially creating a timeline of cosmic bombardment, understanding how these random events have repeatedly acted as a metronome, setting the pace for evolution by clearing the stage and allowing new actors to emerge. This history has even influenced our own human story. Some anthropologists have proposed that a much smaller impact or airburst over North America around 12,800 years ago may have contributed to the sudden cooling of the Younger Dryas period, which could have disrupted the Clovis culture and affected patterns of early human migration across the continents. Perhaps one of the most surprising twists in this story is how these ancient sites of destruction have become sources of incredible creation and wealth. The same immense forces that create an impact crater also create unique geological conditions that can concentrate valuable minerals. The Sudbury Basin is again a prime example. The impact that formed it was so powerful that it melted the Earth's crust and incorporated metals from the impacting body itself, creating a massive ore deposit that has become one of the world's most productive mining districts for over a century, supplying a significant portion of the planet's nickel, copper, and platinum group metals. Similarly, the Chicxulub crater, the dinosaur killer itself, is thought to have created a vast network of hydrothermal systems in its wake. As the crater cooled, these circulating hot fluids may have deposited valuable minerals and even helped to seal and trap oil and gas reserves in the porous, fractured rock below. This incredible transformation, from a moment of utter devastation to a source of the very resources that power our modern civilization, is a powerful testament to the planet's ability to heal and to the unexpected ways in which the cosmos continues to provide for us, reminding us that even in the deepest scars, there can be hidden treasure. But the story of Thea doesn't end with the moon coalescing in orbit. The prevailing giant impact theory suggests that most of Thea was vaporized and thoroughly mixed with Earth's own vaporized mantle material, creating a homogeneous cloud from which both bodies reformed. This would explain the striking isotopic similarities between Earth and Moon rocks that have long puzzled scientists. They seem to be made of the same stuff. But newer, more precise measurements have begun to reveal a fascinating nuance. While the oxygen, titanium, and tungsten isotopes in lunar samples are overwhelmingly similar to Earth's, there are incredibly subtle yet consistent differences. These tiny discrepancies are the ghost in the machine, a faint but persistent whisper suggesting that Thea's unique geochemical signature wasn't completely erased. It's as if we're looking at two nearly identical twins and discovering one has a freckle the other lacks, a tiny mark that points to a different origin. This has led to a breathtaking and revolutionary hypothesis. What if large parts of Thea didn't mix in at all? What if, instead of vaporizing completely, dense chunks of Thea's iron-rich mantle and core sank through Earth's molten outer layers and settled intact, accumulating in vast reservoirs near our planet's core mantle boundary? Scientists have long been aware of two enigmatic continent-sized blobs buried deep within Earth, known as large low shear velocity provinces, or LLSVP. These are massive structures, one beneath the Pacific Ocean and another under Africa, that are revealed by seismic tomography essentially, earthquake waves that slow down dramatically when passing through them, indicating they are denser and hotter than the surrounding mantle rock. For decades, their origin was one of geology's greatest mysteries. Were they simply piles of ancient, sunken oceanic crust, or something far more exotic? The Thea impact theory provides a compelling answer. These dense, thermochemical piles could be the preserved remains of Thea's mantle, a planetary corpse entombed within our own. If true, this means we are not just walking on a planet that was hit by another world. We are literally living above the grave of that world. These buried relics are not passive. They are dynamic, active players in Earth's ongoing geological life. They are thought to be the source of deep mantle plumes, powerful upwellings of superheated rock that fuel the world's most persistent volcanic hotspots, like those that created the Hawaiian Islands or the Iceland Plateau. The composition and location of these Thea-derived blobs could influence everything from the patterns of continental volcanism to the very stability of Earth's magnetic field by affecting the flow of heat from the core. This means an event that occurred 4.5 billion years ago is still actively shaping where volcanoes erupt, how continents move, and how heat escapes from our planet's interior today. This incredible idea transforms our understanding of Earth from a single, isolated planet into a hybrid world, a chimera formed from the union of two distinct planetary bodies. Thea is not just a memory. It is a fundamental part of our planet's architecture, a deep-seated geological force that continues to drive the engine of our dynamic world. The search for its definitive signature is now a driving force in geochemistry and seismology, pushing the limits of our technology to measure ever more minute isotopic variations and to image the deep Earth with greater clarity. Proving this theory would be one of the most profound discoveries in planetary science, finally closing the book on the Moon's origin story while simultaneously opening a new chapter on Earth's deep internal dynamics, revealing that the most violent day in our planet's history left a legacy that is quite literally buried beneath our feet, forever churning and shaping the world we call home. So we've explored how cosmic collisions have been a creative force, shaping our solar system and even seeding the ingredients for life itself. But this grand narrative of celestial violence also presents us with one of the most profound and unsettling questions in all of science, a puzzle known as the Fermi paradox. Simply put, if the universe is so vast and ancient, with billions of planets that could potentially support life, then where is everybody? Why does the cosmos seem so silent? The very prevalence of the impact events we've been discussing might hold a chilling piece of the answer. It suggests a universe that isn't just creatively violent, but inherently dangerous, a place where existence is a fragile and fleeting state. Consider the timeline of our own planet. For over 70% of Earth's history, life existed only as simple, single-celled organisms. The journey from those first microbes to a technological civilization capable of looking up at the stars and wondering about its place in the cosmos took billions of years. It required an unbroken chain of stability, a period free from a planet-sterilizing impact. We now know that such cataclysms are not rare flukes. They are a fundamental part of how planetary systems work. An asteroid like the one that wiped out the dinosaurs strikes Earth on average about once every 100 million years. A larger, more devastating impact that could boil the oceans and reset the clock for all life might happen every few 100 million years. Gamma-ray bursts, the universe's most powerful explosions, could randomly sterilize entire galaxies of complex life. This presents a terrifying possibility that the great silence we hear might be the silence of graveyards. Countless alien civilizations may have arisen on other worlds, only to be wiped out by a random cosmic catastrophe before they could ever develop the technology to announce their presence to the galaxy or to defend themselves from such threats. In this view, survival is not just about intelligence, it's about incredible long-term luck. This idea is a key part of a concept known as the Great Filter, a hypothesized stage in the evolution of life that is so improbably difficult to overcome that it explains why we see no one else. The filter could be behind us, something we've already passed, like the miraculous jump from non-living chemistry to the first self-replicating life. Or it could be ahead of us, a challenge so formidable that virtually no civilization survives it. The constant barrage of cosmic threats presents a compelling candidate for a filter that lies in our future. Perhaps the reason we don't see advanced civilizations is because they all eventually get hit by something they cannot stop, a fate that may still await humanity unless we can change our own odds. But there is a more hopeful and perhaps even more awe-inspiring alternative to this grim scenario. What if some civilizations do make it through? What if, instead of being victims of cosmic violence, they learn to master it? A species that survives long enough to become a spacefaring power would almost certainly have developed robust planetary defense systems, the kind we are only just beginning to imagine. They wouldn't just be looking for asteroids to deflect, they might see them as opportunities. They could harness the raw materials of these celestial bodies, mining them for resources to build vast orbital habitats or fuel their journeys to the stars. In this perspective, the same impacts that are a threat to nascent life could become the stepping stones for a mature, interstellar civilization. The silence we perceive might not be silence at all, but the quiet hum of societies that have long since graduated from broadcasting simple radio waves into the void, having moved on to technologies and modes of communication we cannot yet even conceive of or detect. This dual possibility fundamentally reshapes how we should approach the search for extraterrestrial intelligence, or SETI. It tells us that we shouldn't just be listening for radio signals, we should also be looking for signs of cosmic engineering. Could we detect evidence of a successful asteroid deflection around another star, or the spectral signature of a mining operation on a distant asteroid belt? The evidence of other civilizations might not be a message but a megastructure, a testament to their victory over the chaotic forces that shaped their world. The search for life becomes not just a biological quest, but an archaeological one, sifting through the cosmos for clues about who has survived the universe's trials and how they did it. Our own efforts to track near-Earth objects and test deflection technologies, like the DART mission, then take on a much deeper significance. We are not just protecting our planet for the next century, we are taking our first tentative steps toward passing a test that the universe seems to give to every intelligent species. We are fighting to ensure that our voice, which has only just begun to whisper, is not silenced before it can ever truly be heard. This new power to deflect an asteroid, to literally nudge a celestial body off its course, thrusts humanity into an ethical landscape we have never had to navigate before. The technical challenge is immense, but it pales in comparison to the profound political and moral questions that come with it. If a single nation or even a private company develops the capability to alter the path of an asteroid, who grants them the authority to act? The decision to deflect a planet killer seems obvious, but what about a smaller asteroid, one that might only devastate a continent or a single country? The calculations involved in a deflection are incredibly complex. A small error in planning or execution could inadvertently shift the impact point from one uninhabited region to a major population center halfway across the globe. A mission intended to save millions could, through a miscalculation, end up dooming them instead. This isn't a hypothetical scenario. It's a terrifying responsibility that comes with playing celestial billiards with real human lives as the stakes. The very notion of national borders becomes absurd when facing a threat from space. An asteroid doesn't recognize treaties or sovereignty. Its path of destruction is dictated by pure physics. Yet our response would have to be coordinated by a world still deeply divided along political lines. Imagine the international crisis that would erupt if one country, acting unilaterally, attempted to deflect an asteroid and accidentally caused it to hit a rival nation. The act, intended to be one of global salvation, could be interpreted as an act of war using an asteroid as a weapon. This creates a paradox where the technology meant to ensure our collective survival could itself become a source of catastrophic global conflict. The fear isn't just about failure. It's about the perception of malice, where a technical accident could ignite a political firestorm with unimaginable consequences. This forces us to confront a fundamental question about our species' maturity. Can we set aside our earthly disputes to manage a threat that truly affects all of us equally? This is why the development of planetary defense must be accompanied by the creation of robust, transparent, and inclusive international frameworks. We need clear protocols established long before a threat is ever identified. Organizations like the United Nations Committee on the Peaceful Uses of Outer Space are already working on preliminary guidelines, but these efforts need to be accelerated and given real authority. The process must involve every nation, not just the spacefaring few. Decisions cannot be made behind closed doors by a single government or a corporate board. We need a global consensus on when to act, how to act, and who bears responsibility for the outcomes, both intended and unintended. This requires an unprecedented level of data sharing, trust, and cooperation. Building a system where the world's best scientists and engineers can collaborate without political interference to determine the safest course of action for all of humanity. Ultimately, the ethical challenge of planetary defense holds up a mirror to our own civilization. It tests our capacity for global governance and our ability to act as a unified species. The cosmic threat becomes a forcing function, compelling us to evolve our political structures beyond 20th century models to meet a 21st century challenge. It presents us with a stark choice. Will we succumb to our old habits of suspicion and competition, potentially turning our salvation into our destruction? Or will we rise to the occasion, leveraging our shared intelligence and shared vulnerability to create a new model of international collaboration? The way we answer these questions will reveal more about our readiness for the future than any technological achievement. It will show whether we are merely an intelligent species or a wise one capable of stewarding our own survival together. This grand cycle of cosmic violence and renewal isn't confined to the distant heavens. its fundamental pattern is echoed in the very story of life on our own planet. Think about biological evolution for a moment. For over 150 million years, the dinosaurs were the undisputed masters of the Earth. There reigned a period of relative stability and order. Then, in a geological instant, that order was shattered by a cosmic collision. The impact winter that followed was a catastrophic reset, a wave of destruction that wiped the slate clean. But from that chaos, a new complexity emerged. The extinction of the giant reptiles opened up vast ecological niches, allowing our small, shrew-like mammalian ancestors to venture out from the shadows. Without that disruptive event, the incredible radiation of mammal species leading to primates and eventually to us might never have occurred. The same principle applies to smaller scales. A forest fire, while devastating, clears out old growth and allows sunlight to reach the forest floor, triggering a burst of new life from seeds that have been waiting for their chance to sprout. Destruction, in this cosmic sense, is not an end. It is a necessary clearing away of the old to make room for the new and more complex to arise. This same dynamic of creative destruction is the engine of human progress. Our technological and social evolution is not a smooth, linear climb. It is a story punctuated by disruptive ideas that collide with and shatter established paradigms. The invention of the printing press didn't just improve upon scribes. It shattered the monopoly on knowledge, leading to the Reformation, the scientific revolution, and the Enlightenment. The disruptive collision of digital technology with analog systems has completely reshaped how we communicate, work, and live, creating complexities and connections that were unimaginable just a few decades ago. Every major leap forward is preceded by a breakdown of the old order. This isn't a comfortable process. It involves uncertainty, conflict, and the painful obsolescence of things we hold dear, but it is an essential one. It is the societal equivalent of a supernova, scattering the elements of old ideas so they can recombine into new and more powerful forms. What this reveals is a profound truth about the nature of existence itself. We often see chaos and order as opposing forces, with order being the desired state and chaos being the enemy to be controlled. But the universe teaches us that this is a false dichotomy. True, lasting complexity cannot arise from perfect, static order. A system that is too ordered becomes rigid, stagnant, and ultimately fragile. It is the interplay between the two, the constant tension between the forces of stability and the forces of upheaval, that drives the emergence of truly complex and resilient structures. A galaxy that never experiences mergers remains a bland, gas-poor elliptical, unable to birth new stars. An ecosystem without periodic disturbances becomes monocultural and vulnerable. A society that resists all change eventually collapses under its own inertia. The chaos introduced by cosmic collisions, by extinction events, by disruptive technologies, is not a flaw in the system. It is the system's primary innovation mechanism. It is the universe's way of breaking its own patterns to create something new, something that could not have been predicted from what came before. Our entire existence, from the atoms in our bodies to the societies we've built, is a product of this beautiful, violent, and essential dance between chaos and complexity. Our transition from passive observers to active participants in the cosmic arena is now being powered by a new generation of missions, each designed to address a critical piece of the puzzle. Leading the charge in planetary defense is NASA's Surveyor, a space telescope specifically engineered to hunt for asteroids from the vantage point of space. Unlike ground-based observatories that are limited by daylight and weather, Surveyor will operate in the infrared spectrum, allowing it to detect the heat signatures of asteroids rather than relying on reflected sunlight. This is a game changer, as it will finally allow us to peer into regions of the sky previously blinded by the sun's glare, where many potentially hazardous objects hide. Its sole purpose is to complete the census of near-Earth objects larger than 140 meters, giving us the comprehensive early warning system we desperately need to have decades, not just days, to prepare for a potential threat. But finding an object is only the first step. We must also understand what it's made of. This is where the European Space Agency's Hera mission comes in, serving as the vital follow-up investigation to NASA's groundbreaking DART test. While DART proved we could hit an asteroid and change its orbit, Hera will perform a detailed forensic analysis of the aftermath, traveling to the same binary asteroid system, Didymos and its moonlet Dimorphos. Hera will meticulously measure the mass, composition, and the precise crater left by the DART impact. These details are not just academic, they are the essential data required to turn a one-time experiment into a reliable, scalable planetary defense technique. By understanding exactly how the asteroid responded to the impact, scientists can refine their models and predictions, ensuring that if we ever need to deflect a real threat, we know exactly how much force to apply and where to aim. While these missions look to protect our future, others are delving deep into our past. The Osiris Rex and Hayabusa 2 missions have already achieved what was once pure science fiction, successfully touching down on the asteroids Bennu and Ryugu and collecting precious samples of their primordial material. These are not just rocks, they are time capsules preserved in the deep freeze of space for over 4.5 billion years, completely unchanged by the weathering and geological processes that have altered every stone on Earth. The initial analysis of these samples has been nothing short of revolutionary, revealing a stunning complexity of organic compounds and water-bearing minerals. Each tiny grain is a page from the original recipe book of the solar system, offering direct clues about how water and the building blocks of life were distributed to the inner planets. This research is rewriting our understanding of the early solar system and solidifying the connection between these ancient bombardments and our own existence. This surge of public exploration is now being joined by a wave of private ambition, fundamentally expanding our relationship with these celestial bodies. Companies like Astroforge and Planetary Resources are pioneering the concept of asteroid mining, viewing these rocks not as threats but as treasure chests. The economic potential is staggering. A single metallic asteroid could contain more platinum group metals than have been mined in all of human history, materials critical for everything from electronics to catalytic converters. Beyond metals, water-rich asteroids are seen as the future gas stations of space. By extracting and splitting water into hydrogen and oxygen, these celestial depots could provide the rocket fuel needed to sustain a permanent human presence beyond Earth, turning the asteroid belt into the strategic highway for the next era of space exploration. This marks a profound shift from seeing asteroids as objects of fear to recognizing them as resources of immense value, a necessary step for humanity to become a truly spacefaring species. Together, these public and private endeavors represent a fundamental maturation in our cosmic perspective. We are no longer simply watching the sky and hoping for the best. We are building the tools to find threats, developing the technology to deflect them, studying the origins of our own world, and laying the groundwork to utilize the resources these objects contain. This is a holistic approach to cosmic coexistence, one that learns from the violent past revealed in ancient craters to actively secure a future where humanity thrives both on Earth and among the stars. It's almost overwhelming to consider that every atom in our bodies, every mountain on our planet, and every star in the sky can trace its origin back to a series of unimaginably violent cosmic accidents. This perspective suggests we are here by a fluke, the winners of a cosmic lottery with odds so astronomically low that our existence feels like a beautiful, temporary glitch in a vast and mostly empty universe. If that asteroid had missed Earth 66 million years ago, mammals might still be scurrying in the shadows. If Thea had struck our planet at a slightly different angle, we might have no moon, no stable tilt, and no seasons to drive the evolution of complex life. This view of cosmic randomness can be both humbling and terrifying, reducing our story to one of sheer, undirected chance where humanity is merely a fleeting spark in the endless dark. Yet there's another way to look at this same evidence, one that finds a strange kind of order within the chaos. While each individual collision is a random event, the laws of physics and chemistry that govern them are not. Gravity will always pull matter together. Nuclear fusion will always forge heavier elements in stellar cores, and given the right conditions, a rocky planet in a habitable zone, a constant bombardment of water-rich comets, and a large moon to stabilize the climate, the emergence of complexity might not be an accident at all, but a natural outcome. In this view, the universe isn't random, it's productive. It has a built-in tendency to create ever more complex structures, from galaxies and stars to planets and, eventually, life. The violence isn't meaningless destruction. It's the universe's method of construction, a relentless hammer that forges islands of order out of a sea of chaos. This isn't about a predetermined destiny, but about a universe that is inherently bio-friendly, with the potential for life written into its fundamental laws. This tension between accident and inevitability is one of the oldest and most profound debates in human thought, and it echoes far beyond the realm of science. For some religious and spiritual traditions, the precise fine-tuning of the universe, where physical constants are set exactly right to allow for our existence, is powerful evidence of a divine architect, a creator who set the stage for life to emerge. In this narrative, cosmic collisions are not random acts but instruments in a grand, intentional design. Conversely, many philosophical schools of thought, like existentialism, find profound meaning in the very absence of a plan. If our existence is a product of chance, then we are truly free to create our own purpose and meaning, to define our own destiny without reference to any preordained cosmic script. Our value isn't given to us, it is chosen by us, making our lives a project of our own creation. What's truly fascinating is that modern science doesn't cleanly resolve this debate. It lives within the tension itself. The theory of punctuated equilibrium in evolution, for example, shows that long periods of stability are shattered by sudden, disruptive events that accelerate change. This mirrors the cosmic story, where billions of years of peaceful orbital mechanics are interrupted by planet-altering impacts. Both narratives suggest that progress isn't always a slow, steady climb, but a story of stability shattered by chaos, which in turn creates new opportunities for even greater complexity to emerge. This pattern seems to be a fundamental feature of our universe, from the smallest biological scale to the largest cosmological one. So perhaps the question isn't whether we are products of accident or destiny, but both. We are the result of a universe that is lawful enough to create the conditions for life, but chaotic enough to allow for freedom, surprise, and genuine novelty. This shifts our role from passive bystanders to active participants. Understanding that cosmic violence shaped us doesn't mean we are helpless in the face of future chaos. Instead, it empowers us. Our knowledge of asteroids allows us to track them and develop plans to deflect them. Our understanding of stellar evolution tells us our sun will eventually die, pushing us to look toward the stars and dream of a future beyond our solar system. We are the universe become self-aware, capable of looking back at the processes that created us and choosing to steer them toward a future we desire. We are no longer just subjects of cosmic forces. We are agents who can begin to shape them. This doesn't answer the metaphysical question of whether it was all meant to be, but it does answer the human question of what we do next. Our purpose, then, might be found not in deciphering some hidden cosmic plan, but in embracing our unique responsibility as the first known creatures who can understand this story and choose to continue it. The story of our cosmic origins, filled with cataclysmic drama and profound wonder, is one of the most powerful tools we have to ignite a passion for discovery in the next generation. It's not just about memorizing facts from a textbook. It's about connecting young minds to the grand, dynamic narrative of the universe, a story in which they themselves are active characters. By framing science through the lens of these epic collisions, the violence that built our world and the ongoing vigilance required to protect it, we can transform abstract concepts into a thrilling saga of survival and exploration. This approach makes the fields of science, technology, engineering, and mathematics, or STEM, feel less like distant subjects and more like essential toolkits for understanding our place in the cosmos and ensuring our future within it. This inspiration takes shape in wonderfully hands-on ways through global citizen science initiatives. Programs like NASA Asteroid Data Hunter allow students and amateur astronomers to analyze real data from telescopes, actually contributing to the effort of finding and tracking near-Earth objects. Imagine a high school student working from their laptop, becoming the first person to ever notice the faint, moving pixel of a previously unknown asteroid. That moment of discovery is transformative. It's no longer just learning about science, it's doing science. It creates a direct personal connection to a global endeavor, showing young people that their curiosity and effort can have a tangible impact on a planetary scale. This participatory model demystifies the scientific process, revealing it as a collaborative, ongoing human adventure rather than a static collection of settled facts. Beyond the computer screen, immersive experiences in planetariums and museums bring the awe of the cosmos directly to the public. Modern digital domes can simulate the formation of the moon from the collision with Thea with breathtaking visuals, allowing audiences to witness the birth of our closest celestial companion. They can recreate the Chicxulub impact not to sensationalize destruction, but to soberly illustrate the delicate balance of our biosphere and the powerful forces that can reshape it. These shows are powerful because they engage our emotions and our senses, creating a visceral understanding of scale and time that a textbook paragraph simply cannot match. They contextualize the night sky, turning familiar points of light into characters in an ancient story of creation and change. Of course, teaching about existential risks requires a careful, responsible approach. The goal is never to frighten, but to empower through knowledge. This means presenting the facts clearly and without hype, explaining the difference between a city-killer asteroid and a global catastrophe, discussing the realistic probabilities involved, and most importantly, highlighting the solutions being developed. When we talk about the DART mission's success in altering an asteroid's orbit, we're not just teaching orbital mechanics, we're teaching problem solving on the grandest possible scale. This honest, solutions-focused education builds a resilient and informed public, one that can support reasoned policy and fund planetary defense initiatives without succumbing to either panic or complacency. It replaces anxiety with agency. Ultimately, this educational mission is about fostering a new kind of cosmic literacy. It's about ensuring that future generations inherit not just a catalog of risks, but a deep appreciation for the beautiful, violent, and interconnected processes that crafted our world and the life upon it. This knowledge equips them to be both thoughtful explorers and diligent guardians. They will be the scientists who improve our detection algorithms, the engineers who design the next generation of deflection technology, the policymakers who foster international cooperation, and the voters who understand why looking up at the sky is a critical part of taking care of our Earth. By sharing this story, we pass on the most crucial tool of all, the wisdom to navigate a universe of both wonder and peril, ensuring that humanity's journey continues for generations to come. The story of cosmic collisions is a powerful reminder that knowledge does not exist in a vacuum. The most profound breakthroughs in understanding our existence often occur at the blurry boundaries between traditional scientific disciplines, where experts from vastly different fields come together to solve a shared puzzle. This is the beautiful, collaborative reality of studying these ancient impacts. It shatters academic silos and forges connections that reveal a far richer picture of the universe than any single lens could ever provide. Consider the humble impact crater. To an astronomer, it's a surface feature, a scar that helps date a planet's surface, but to a geologist, that same crater is a treasure trove. The intense heat and pressure of the impact create unique minerals like shocked quartz and stishovite, which are never formed by volcanic activity. These minerals act as a definitive fingerprint, allowing geologists to confirm an impact's origin and even estimate its immense force. Then a climate scientist enters the picture. By analyzing the layers of sediment within and around the crater, they can extract a detailed record of how the event altered the global climate. The fine dust and aerosols injected into the atmosphere would have blocked sunlight, and the chemical isotopes trapped in the rock layers tell a story of global cooling, acid rain, and a dramatic shift in Earth's environmental conditions. A single crater, therefore, becomes a multidisciplinary archive, holding secrets for experts in rocks, climates, and planetary history. The connections extend deep into the realm of chemistry and biology. When the Osiris-Rex mission returned a sample from the asteroid Bennu, that capsule of pristine space rock did not go to a single laboratory. It was distributed to teams of chemists who analyzed its complex organic molecules, to mineralogists who studied its water-bearing clays, and to astrobiologists who searched for the prebiotic building blocks of life. The discovery of amino acids and other organic compounds on such a primitive body is a stunning piece of evidence that the raw ingredients for biology are widespread throughout the solar system. This finding bridges the gap between the inorganic chemistry of space and the organic chemistry of life, suggesting that the universe might be pre-loaded with the necessary components for biology to emerge wherever conditions allow. A cosmochemist's analysis of a space rock directly informs an astrobiologist's model for how life might have started on Earth or could start elsewhere. Even the social sciences and humanities are woven into this tapestry. The psychological and cultural impact of cosmic violence, from ancient myths about fiery chariots in the sky to modern blockbuster films about asteroid impacts, reveals a deep-seated human awareness of these threats. Sociologists study how this awareness influences public policy and international cooperation around planetary defense, while historians might examine how past civilizations interpreted comets and meteor showers as omens, shaping the course of human events. The ethical dilemmas surrounding asteroid deflection, who decides to act and who bears responsibility for the consequences, are not questions for engineers alone, but for philosophers, ethicists, and political scientists. This demonstrates that the challenge of cosmic collisions is not merely a technical problem. It is a human one, requiring a fusion of scientific capability and societal wisdom. This holistic, interdisciplinary approach is where true innovation is born. When a planetary scientist with expertise in orbital mechanics collaborates with a materials engineer to design a spacecraft shield, they create technology that is far more effective than either could have conceived alone. When data from a space telescope hunting for near-Earth objects is made available to citizen scientists and amateur astronomers around the world through open-source software, the pace of discovery accelerates exponentially. This breaking down of barriers allows for a cross-pollination of ideas, where a technique developed for one field can provide the missing key for another. It proves that the universe does not care for our man-made categories of knowledge. To truly understand our place within it, we must be willing to follow the clues wherever they lead, weaving together every strand of insight from every corner of human inquiry into a stronger, more complete understanding of the cosmos we call home. While giant telescopes and space agencies capture the headlines, there exists a vast, distributed network of eyes on the sky that forms the indispensable first line of planetary defense, the global community of amateur astronomers. These dedicated enthusiasts, armed with their own telescopes, cameras, and a deep passion for the cosmos, are far more than just hobbyists. They are vital citizen scientists, contributing countless hours and a wealth of data that professional observatories simply could not match on their own. Their strength lies in their numbers and their positioning. With backyards and private observatories scattered across every continent, they provide a continuous 24-hour watch on the heavens, filling in the observational gaps left by the day-night cycle and weather that can temporarily blind the world's major professional facilities. This ground-level vigilance is crucial for tracking the faint, fast-moving objects that might otherwise slip through the cracks. This collaborative effort is powerfully organized through official programs designed to harness this public passion. The International Astronomical Union, through its Minor Planet Center, acts as the central clearinghouse for these discoveries. They provide the software, the training protocols, and the official channels for amateurs to report their findings. Initiatives like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, project incorporate data from a worldwide network of amateur contributors to supplement its own robotic telescopes. Other programs, such as NASA's Citizen Science Asteroid Data Hunter, provide software that allows anyone with a computer to analyze telescope images and search for the telltale streaks of moving asteroids, turning a global army of volunteers into a powerful data processing force. This formalizes the process, ensuring that a curious sighting in someone's eyepiece doesn't just remain a personal anecdote, but becomes a validated data point in a global security system. The impact of this democratized science is measured in very real discoveries. A significant percentage of new comets are found by amateurs, who often bear the discoverer's name as a permanent honor, like the famed Shoemaker-Levy 9 comet. More importantly, they are frequently the first to spot and track newly discovered near-Earth asteroids, providing the critical initial data that allows professionals to calculate an object's orbit and assess its potential risk. This early warning is everything. The sooner an object is found, the more time we have to study it and, if necessary, plan a deflection mission. Their work doesn't stop at discovery. Many amateurs specialize in follow-up observations, meticulously measuring the position and brightness of known objects night after night. This data is essential for refining orbital calculations, ruling out potential future impacts, or confirming that an object does indeed require our attention. Beyond the raw data, this movement builds something perhaps even more valuable: a truly global community united by a shared purpose. Online forums, social media groups, and annual star parties buzz with conversations about orbital mechanics, astrophotography techniques, and the latest observations. A retiree in Arizona might share his data with a university student in Chile, who then collaborates with an amateur in Japan to track an object as it passes through the night sky. This breaks down not only geographic barriers but also the perceived barrier between professional scientists and the public. It fosters a profound sense of shared guardianship, a collective understanding that protecting our planet is not a task for a select few in lab coats, but a responsibility that we all can and should participate in. In an era where humanity's future is increasingly tied to space, these citizen scientists are our most watchful sentinels, proving that the most advanced technology in the world is still no match for the power of a curious human mind looking up at the stars. From the titanic impact that carved our moon from Earth's molten flesh to the fiery asteroid that cleared the stage for our mammalian ancestors, we have traced a story written in violence and sculpted by chaos. These are not mere historical footnotes. They are the fundamental forge fires in which our planet, our biology, and our very atoms were shaped. We stand here today as living testament to a universe that builds not only through gentle accretion but through catastrophic creative destruction. A cosmos where the same hammer that shatters a world can also pound out the delicate instruments of life. Our existence is a beautiful, improbable scar on the face of eternity, a permanent record of countless forgotten collisions. This grand narrative binds us to the cosmos in the most intimate way imaginable. The iron in your blood, the calcium in your bones, the very air you breathe, all were either delivered or forged by these ancient acts of celestial violence. We are not just living in the universe is living within us. We are walking, talking archives of stellar explosions and planetary crashes, a collection of cosmic artifacts that has learned to look back at the stars and wonder about its own origins. This perspective transforms our place in the cosmos from one of lonely isolation to one of deep, fundamental connection. We are the universe becoming self-aware, beginning to comprehend the magnificent and terrifying processes that led to our moment in the sun. This legacy is not just about understanding the past, it is our essential guidebook for the future. The same cosmic processes that gifted us life hold the potential to take it all away. The craters on the moon and the scars on our own planet are silent reminders that the solar system remains an active shooting gallery. Our newfound knowledge of this history comes with a profound responsibility. The duty to protect the fragile world that these collisions so miraculously made habitable. This means vigilantly tracking near-Earth objects, developing technologies to deflect them, and fostering unprecedented international cooperation to ensure that when a threat is identified, humanity can respond as a united species. Our survival depends on transforming our understanding of cosmic violence into a practical blueprint for planetary defense, but our mission extends beyond mere survival. This knowledge is an invitation to participate actively in the next great chapter of our cosmic story. By venturing out to asteroids and comets, by studying the formation of other solar systems, and by searching for the signatures of life on distant worlds, we are no longer passive subjects of cosmic forces. We are becoming active participants, using the intellect that the universe bestowed upon us to unravel its deepest mysteries and secure our place within it. The story of cosmic collisions teaches us that we are the products of both incredible chance and universal physical laws, a combination that grants us both humility and agency. So as you go about your day, remember the incredible journey encoded in your every cell. Remember that you are made from the debris of ancient stars and the fragments of vanished worlds, brought together by a symphony of impacts that spans billions of years. This is our shared inheritance, a story of violence and beauty, chaos and order, destruction and creation. It is a story that continues to unfold, and we all have a role to play in its next paragraph. Thank you for exploring these profound mysteries with me. If this journey through space and time resonated with you, feel free to subscribe for more adventures into the unknown, and I'd love to hear your thoughts and reflections in the comments.